Okay, let's recall what we talked about last time, namely the Gram-Schmidt process. Okay, so the setup is W is a subspace of Rn. Let's say the dimension is P, and suppose we are given a basis of W, then the process constructs an orthogonal basis of W as follows: obtain an orthogonal basis U1, U2 through UP of W given as follows. Okay, start with U1 is W1, U2 is W2 minus some portion of U1, so W2 dot U1 over U1 dot U1 times U1. Okay, and U3 is W3 minus some portion of U1 minus some portion of U2, and the numbers are as follows. U2 dot U2 here. So this is W3 dot U1 divided by U1 dot U1, and W3 dot U2 divided by U2 dot U2. And in general, for every I from 2 up to P, Ui is given by modifying Wi by subtracting it the following thing. Some portion of UK where K goes from 1 to I minus 1. The portion is UK dot UK in the denominator, Wi dot UK in the numerator. Okay. So, and we've talked about how you may want to remember this. Basically, once you've decided to construct the U's by modifying the one after another, by modifying the W's in this fashion, it's easy to determine what these numbers you want to put. So now let's look at some examples just to see how this process works in action. So say you have two vectors, W1, 1, 1, 2, W2, 0, 2, minus 4, and suppose W is the span of these vectors, W1 and W2, which is a subspace of R3. And so first of all, we notice that W1 and W2 are linearly independent. And for this, you just check that AW1 plus BW2 equaling 0 has only the trivial solutions for A and B. And this you can see just by explicitly writing out AW1 plus BW2. That's A plus 2B, 2A minus 4B, equaling the 0 vector 0, 0, 0. And this forces immediately that A is 0. And once A is 0, any of the other two equations will give you B equal to 0. So the two vectors are linearly independent, and the subspace W is the span of these two vectors. Therefore, the two vectors give you a basis. So W1, W2 is a basis of W. And now we will apply the Gram-Schmidt process to obtain an orthogonal basis as follows. Okay. So what do? We take U1 to be W1. So that was 1, 1, 2. Now U2, according to the construction, should be W2 minus some multiple of U1, and the multiple being given by W2 dot U1 over U1 dot U1. Okay, so we can now be explicit about this. W2 is 0 to negative 4 minus U1 is W1, so that's 1, 1, 2. Now the number we need to put here, U1 dot U1 is 1 plus 1 plus 4. Okay. W2 dot U1, so that's just U1 dot U2. So, sorry, that's just W1 dot with W2. So that is 0 plus 2 minus 8. Okay. So that comes out to be 0, 2 minus 4 minus 6, negative 6, 1, 1, 2. 1, 1, 2. So this is just minus 1. So together with a minus in front of it, you get a plus. So you just have this vector plus 1, 1, 2. So that is 1, 3, 2. 1, 3, negative 2. Okay, so this is it, because the dimension of the subspace is 2. And we check that U1 dot U2 is indeed 0, so that this is indeed a orthogonal basis. U1 dot U2 is 1 plus 3 minus 4, which is 0. So that is good. Okay, that's one example. Oops. Now let's try another example. Say I have this time 3 vectors. Certainly more complicated. W2 being 0, 1, 3, 1. W3 being 1, 1, 1, 0. And W is the span of these vectors. This is a subspace of R4. Okay. So first things first, we still have to check that these guys, W1, W2, and W3 form a basis of W. They already span W, so we need them to be linearly independent. And that's a straightforward thing to check, but it still needs to be checked. So we do that. So we consider the linear combination AW1 plus BW2 plus CW3 being 0. This is the same as what we get by writing it out explicitly. So A, let's see here. So the first entry would just be a C. Then the second entry is A plus B plus C. Third entry is 2A plus 3B plus C. Last entry is A plus B equal to the 0 vector. Okay, and we certainly see a system of linear equations in 3 unknowns here. Well, we can use the method we've discussed to solve for it, but we can also take advantage of the special form of these equations and immediately conclude that C is 0. And then, we can see that when C is 0, the third equation becomes 2A plus 3B equals to 0. Last equation is A plus B equals 0. So now these two equations together give you that A is negative 3/2 B and A is negative B. And the only way for that to hold is for both A and B to be 0. Okay, so it is indeed a linear independent set of 3 vectors. So now we apply the Gram-Schmidt process to obtain from this orthogonal basis. So we need 3. So we're going to get U1, U2, and U3, where U1 is given as W1 by construction. U2 is W2 minus some multiple U1, W2 dot U1 divided by U1 dot U1. Okay. So we need to compute this explicitly because we're going to need it for U3. Okay, so let's do that. W2 is 0, 1, 3, 1 minus the sum number here. U1 is W1, so 0, 1, 2, 1. And U1 dot U1 is 1 plus 4 plus 1. W2 dot U1, that's W2 dot W1. That's 1 plus 6 plus 1. Yes. So we end up having 0, 1, 3, 1 still minus this is 8 divided by 6, so 4 on 3, 0, 1, 2, 1. So that comes out to be 0, 1 minus 4/3, negative 1/3, 3 minus, that's 1/3, and 1 minus that is again minus 1/3. Okay. Yes, this is U2. So this is what comes out to be U2. Okay, now for U3, it's by construction W3 minus some multiple of U1 minus some multiple of U2. Okay, and the multiples are U1 dot U1, W3 dot W1, oh sorry, U1, W3 dot U2, U2 dot U2. Okay, and now we can compute. W3 is 1110 minus U1 dot U1 is again 1 plus 1 plus 4 plus 1. W3 dot W3 dot U1 is let's see 1 plus 2. Okay, and we have U1 here. That's 0, 1, 2, 1. And then we also have U2 dot U2. This is U2, so that's going to be messy. So 1 nice plus 1 nice plus 1 nice. That's U2 dot U2. W3 dot U2 is, well, let's see here. W3 is 1110, and dotting this, you get negative 1/3 plus 1/3. And the vector is still 1110. Now, this is a little bit simpler than we thought because this number here is 0. So hence the whole last term goes away. But the other bit still remains 1110 minus so it's 3 divided by 6, so a half 0, 1, 2, 1. So that's 1 minus a half, 1 minus 1, 0, 0 minus a half. Okay. So now we get the 3 vectors computed, and you can check easily by hand that they are indeed, these 3 vectors are indeed pairwise orthogonal. So we get a orthogonal basis. Very good. So this is how the Grand-Schmidt process is applied. And in general, if you are handed, and basically when you are asked to apply the Grand-Schmidt process, you just do this. It's gonna involve some lengthy computations in general, but nothing that you cannot do. Okay, so now we're gonna move on to consider the next topic, the notion of linear transformation. Okay, so let's consider the definition right away. So suppose V is a subspace of Rn and W is a subspace of Rm. Okay, a linear transformation from V to W is a function. Let's call it T. That goes from V to W. So everything in V is sent by T to a something in W is a function such that two properties hold for U, V in V, and A in R. We have T U plus V. Right? Having two vectors in V, I can certainly consider U plus V. And the function T will take it to something in W. I can also consider T of U and T of V. Both are vectors in W, and I can ask for the sum. And one of the requirements for being a linear transformation is T of U plus V is T of U plus T of V. The other requirement is that T applies to the vector A times U is the same as A times T of U. Okay. So these two are the requirements for being a linear transformation. In some sense, you can say that a linear transformation, the requirements here are just saying that the function T is compatible with the vector space operations. Okay. Let's look at some examples. So first of all, there is the most extreme example. T go from V to W. T sends every vector to the zero vector. Okay, and this is a linear transformation. And to see this, we just have to verify the two required properties. So we have to consider T for U and V, T of U plus V, and TU and TV. Right, but by definition, T sends everything to zero. So this is just 0 and 0 and 0. So, and we know that the zero vector satisfies the property that 0 equals to 0 plus 0. So the first requirement is certainly true. Now, for the second requirement, we have to look at T of AU and A times TU. T of AU is again by definition of T being 0. A times TU is A times 0. And we know that any number times the zero vector is the zero vector. So this requirement also holds. Therefore, we have indeed a linear transformation. Now, let's consider some other example. This is another extreme example where you notice that T is now a function from a subspace V to itself. And the definition of T is T sends a vector U to itself. Okay. And this T is linear or is a linear transformation. And to see this, you again want to check the two required properties, each of which is an equation. So for that, to check them, you compute both sides. Now for T of U plus V is U plus V because T sends U to itself. Now T of U is U, T of V is V. So T of U plus T of V is U plus V. So that's equal to U plus V, no problem. Now T of AU and A times T of U. To compute these two is also straightforward. T of A times U is AU because T sends any vector to itself. So T of U is U. A times T of U is A times U. That's AU. So once again, the property is satisfied. So you indeed have a linear transformation. And this one goes by the name of the identity transformation. Okay. Now, let's look at some more specific example. Say, I don't know, call it T from R3 to R2. T sends a vector x1, x2. Ooh, no. Goes from R3. So T sends a vector x1, x2, x3 to x1 plus x2 plus x3, x1 minus x3. Okay. Let's consider this map or this function. And the claim is that this is a linear transformation. And to see this, we again have to check the required properties. Now this time we have to be specific about, well, not specific, we have to spell out some more details about the inputs. Suppose U and V are given as follows. We can also have some number A. Okay, then we still have to consider T of U plus V and TU and plus TV. Now U plus V is easy to compute because you just add the corresponding entries like these. Now applying T to this, you'll get the following vector, right? T of x1, x2, x3 goes to a two-dimensional vector x1, x2, x1 plus x2 plus x3 and x1 minus x3. So over here we now have for T of U plus V. Like that for the first entry, and for the other entry, minus U3 plus V3, like that. Okay. Now, these two, T of U plus T of V, is a bit easier to determine. So T of U is U1 plus U2 plus U3, U1 minus U3. Similarly for T of V, V1 plus V2 plus V3, V1 minus V3. And if we try to add these two vectors together, we're going to get U1 plus U2 plus U3 plus V1 plus V2 plus V3, U1 minus U3 plus V1 minus V3. And if you just look at these two vectors now, you see that they are equal. Okay, so the first required property is checked out. Now, for the other required property, we have to look at T of A times U and A times T of U. Now, T of A times U is just T of, well, this vector AU1, AU2, AU3, right? That's this, what's inside here is A times U. And now you apply the definition of T right there. So that's giving you AU1 plus AU2, AU3, AU1 minus AU3. Okay. Now for A times T of U, you get A times U1 plus U2 plus U3, U1 minus U3, which is, after you multiply the A into it, A times U1 plus U2 plus U3, A times U1 minus U3. And then if you just look at these two vectors, you see that they're indeed equal. Okay, so again, another example checks out. Okay, now let's look at some non-example. Some base, the function, let's say the function T, I mean, there are even just between R, right? R is itself a vector space. Even just between R, there are many functions that are not linear. So this one, for example, the exponential function is not a linear transformation. Essentially, no required properties hold for this guy. Right? For example, I mean, T of this is never equal to EX plus EY. It's equal to EX times EY. E to the AX is never equal to A times E to the X. So the exponential function is definitely not a linear transformation. Now, there, I mean, maybe you would hope that things that don't involve this sort of special functions are, are always linear transformation. But I mean, even the square function is not a linear transformation. Right, because x plus y square is not x squared plus y squared over r anyway. Ax squared is not a times x squared. Now, even some milder examples are not necessarily linear transformations. So suppose you have the following map or function from R2 to itself, given by sending x1, x2 to x1 minus x2 plus 1, 3x2, say. And this is, the claim is that this is not a linear transformation. And again, again, well, to say that it's not a linear transformation, you just have to exhibit one property that fails. In fact, in this case, both properties would fail, as we can see now. So say you put U to be U1, U2, V, be V1, V2. Okay. Yeah. Okay, then we can compute now T of U plus V and compare it with TU plus TV. T of U plus V is T of U1 plus V1, U2 plus V2, which is now U1 plus V1 minus U2 plus V2 plus 1, 3, U2 plus V2. Okay. Now TU plus TV is U1 minus U2 plus 1, 3U2 plus V1 minus V2 plus 1, 3V2. And we can calculate the sum of these two vectors, U1 minus U2 plus V1 minus V2 plus 2, 3U2 plus 3V2. And now you see that they are not equal because here you have a 2, whereas here you have a 1. They're not equal because these two vectors are not equal. One of the requirements for being linear does not hold. And you can also check that the other requirement also doesn't hold. For that, we want to compare T of AU and A times TU. That's T of AU1, AU2, which is AU1 minus AU2 plus 1. AU2 plus 3 times AU2. Now A times TU is A U1 minus U2 plus 1, 3U2, which is AU1 minus AU2 plus A, 3AU2. And now you see that these two are not equal. Again, by observing that over here you have an A, but over here you have a 1. So they are not equal unless A is 1. Okay, so you're now getting this is not a linear transformation. Now let's look at some linear transformation again. So suppose T is again going from B to itself. So I should begin with fixing the number A in R, and T is V from V to itself defined by sending U to its A's multiple. Okay, so this is a linear transformation. And verification is direct. You compare T of U plus V with TU plus TV. And the computation is fairly straightforward. T of U plus V is A times that, U plus V. TU plus TV is AU plus AV. And the fact that these two are equal is one of the required properties for the vector space operations. So that's fine. Now for now I already have A used, so I use C. So for a scalar multiple, T of CU and C times T of U, we get T of CU is A times CU. C times T of U is C times AU. And these two are equal again because of some requirement for the vector space operations. So we get another example of linear transformations. Now, let's consider one more example. It's a bit of a funny one. So the setup is this: W is a subspace. Say the dimension is denoted by P. And let's pick a basis. W1 through WP basis. Okay. And then define T that goes from Rn to W is defined by the following operation. T of V is given by a linear combination of the W's, W1 dot V of times V W1, W2 dot V times W2, and so on, down to W P times V W2P. Okay. By construction, this expression lives in W because it's a linear combination of the little w's, so it belongs to W because the little w's form a basis. Okay. And this is a linear transformation. And for this, you just have to do those checks again. Again, you have U and V being in the space Rn, and scalar A in R, T of U plus V. And well, let's first of all compute T of U plus V. This is a bit lengthy. W1 dot U plus V as a number times W1. W2 dot U plus V as a number times W2, and so on down to WP dot U plus V times WP. Okay. Now, one of the properties of dot product tells us you can break these dot product as follows: W1 dot U plus W1 dot V, W1, W2 dot U plus W2 dot V, W2, plus WP dot U plus WP dot V, WP. Okay, so that's that. Now we can compute T of U plus T of V. Okay. T of U is W1 dot U, W1, W2 dot U, W2, WP dot U, WP, and plus T of V, which is W1 dot V, W1, W2 dot V, W2, WP dot V, WP. And then you just see by looking at these expressions that these guys, this expression and this expression, they are equal. Okay? Nothing funny about this. You just verify the equality. Now for the other requirement, we have to compute T of A times U, which is W1 dot AU, W1, W2 dot AU, W2, WP dot AU, WP. And now there's another property that you can use about the dot product is when you have a scalar, in this case of these A's, multiplied to your vector, you can pull out that scalar. That'll give you A W1 dot U, W1, A W2 dot U, W2, A WP dot U, WP. Okay. Now, on the other hand, we should compute A times T of U. And that's straightforward. That's just A times W1 dot U, W1, W2 dot U, W2, WP dot U, WP. And then once again, you just examine these two expressions, you see that they are equal, right? After all, if you just distribute the A here, multiplication by A into the terms, you get what's written here. So you indeed have a linear transformation. This guy has a name. This T here, this T is the orthogonal projection onto W. Okay. Anyway. Now, having seen all these examples, let's move on to do some general discussion. So T, let's suppose T going from V to W is a linear transformation. Okay, and if I have AB being real and UV being in V, then I have T of AU plus BV to equal to, well, it's a sum of two vectors I'm applying T to, so I can use the first required property, that is T of AU plus T of BV. Now, the second required property applies to each of the summands, telling us it's A times T of U plus B times T of V. Okay. Now, more generally, if you have V1, you have V1 through VR in V, C1 through CR in R, then you can consider T of C1 V1 plus C2 V2 plus CR VR, right? Then you can first of all, you can break on the terms one after another. That is, you can break it using the first requirement. You can write this as T of C1 V1 plus T of C2 V2 plus everything else. Okay. And C1 V1, T of C1 V1 can be written as C1 times T of V1. Then you repeat the process of breaking off one term at a time to the other term. So you get C2 T of V2 and so on, all the way to CR T of VR. So now what do I want to talk about? So if V1 through VR here is a basis, then being a basis means everything in V, then every vector in V is of the form C1 V1 plus up to CR VR, and T of this vector C1 V1 up to CR VR is given by the above expression. Once we know T of V1, T of V2, and so on up to T of VR, right? So in other words, to describe a linear transformation, what we need here, when we have a basis, all we need to know is how the linear transformation works on basis vectors. Okay, let's look at a simple example to begin with, and then formulate something more general. So suppose, let's say I have a linear transformation from R2 to itself, and given by no, not from R2 to itself, but from R3 to R2. So the linear transformation is given by the following expression on basis vectors. T of E1 is the vector 1, 2. T of E2 is the vector minus 1, 1. T of E3 is the vector 2, 3, say. And describe E. So we can then, for an arbitrary vector X, three-dimensional vector, right? So 3 entries. We can describe T of X as follows. First of all, notice that X is X1 E1 plus X2 E2 plus X3 E3. So T of x is T of x1 E1 plus x2 E2 plus x3 E3, which is, as we discussed above, x1 T of E1 plus x2 T of E2 plus x3 T of E3. And now we can write these out explicitly. T of E1 is given as above, so as T of E2 and T of E3. And that gives us x1 minus x2 plus 2x3, 2x1 plus x2 plus 3x3. So this gives a general description of the linear transformation. Okay. All right. So we gonna stop here for today and continue to next time we'll pick up from here and give us some more general discussion about how you describe linear transformations with a given basis, namely the standard basis. Okay.